Okay, hello everyone. Let's just wait a few minutes so that all the other participants join as well. We are missing two more students, I think. Okay, we still have one missing. Okay, let's start anyway. So, good afternoon and hi. Uh, my name is Amir. Can you hear me? Can you just make a sound so that I know that someone's here and I'm not talking into the void?
Yes, we can hear you, Professor.
Okay,
Yeah,
great.
we can hear you.
So this is going to be a graduate course in programming languages, but it's actually going to be quite an easy one. Uh, so, and the reason behind this is because apparently there are no in-depth programming language courses at the undergraduate level here at HKUST. So we have to basically cover a lot of fundamental stuff. And uh, So let me start by saying that my name is, of course, Amir Goharshady, and you can all call me Amir because my last name is too hard. And uh, let's talk a little bit about this course. So the course is basically going to cover a lot of ground, but these are all basics of programming languages and verification. We start mostly with formal semantics. For example, this session today, I will mostly talk about operational semantics. But as the course progresses, we will go more and more towards verification and less towards programming language theory. So you will not see things like functional programming or type systems in this course. The course is mostly going to be about algorithms that are used for verification. But anyway, at the beginning, we have to still cover some formal semantics. So today we'll start with operational semantics. In the next sessions, we will also talk about two other classical ways of defining semantics, which are denotational and axiomatic. And then after this thing is done, we will switch to the verification side. We will start with something that is uh, pretty nice. It's basically the idea of two-player games on graphs with omega regular objectives. So you will suddenly see a shift from PL to graph algorithms. And at first, this might seem odd, but as the course goes on, you will see that this is actually very much related and needed for our verification purposes. The next major topic that we will cover after two-player games is automata and infinite words. So I expect that from bachelor courses, you are already familiar with uh, automata on finite words, so you should know about uh, deterministic finite automaton and non-deterministic finite automaton. And here I'm going to uh, just tell you about what happens when your input is infinite and infinite word. After that, we're going to talk about LTL. This is towards the end of the course. We talk about linear temporal logic. This is one of the most important and fundamental logics in program verification. And then at this point, you will actually see a convergence of all the material. So you will see that for a single verification task, we can look at it from many different points of view. We can look at it from a game view, a logical view, or an automaton view. And then if time permits, based on how fast we can go, and how fast I go is really dependent on you, I can also cover some more in-depth and modern topics. So I can talk probably about termination analysis and also invariant generation. Uh, so let me start by telling you that you should feel free to interrupt me at any time. And I actually encourage you to do this, because if you don't interrupt me, I will just go super fast. And my assumption is that as long as no one's unhappy, I'm doing a good job and everyone's understanding everything. So as soon as you have a question, please interrupt me. And okay, so I'm going to just tell you a little bit about grading in this course. So there are going to be homeworks, and I will assign the first homework today. The homeworks are quite easy. The main idea behind the homeworks is to make sure that you understand the material in the course itself. And because understanding is the main goal, you actually get to resubmit your homeworks as many times as you like. But don't misuse this, otherwise we will have to put a limit on it. So basically the idea is that every time I assign a homework, you can send your solutions over, and then we will give you comments. You either get the full marks of the homework or you get some comments about what was wrong, and then you can resubmit until you get the whole mark. And towards the end of the course, you will also be asked to read some papers in groups of 4 or 5 and present them. So those presentations also contribute to this 50%. And then we will have a final take-home exam. And this exam is also 50% of the overall grade. And it's a take-home exam. I will give you the exam and you can take your time with it. I'll probably give you 2-3 days of time. Just don't collaborate, do it on your own. I trust you. And overall, this is probably going to be the easiest postgraduate course that you have taken. It's really hard not to get an A plus or an A in this course. And this actually counts as a theoretical course. So that's that. And okay, before I go into the actual material, does anyone have any questions? Nothing? Okay. Great. Uh, so the way this course works is I'm generally going to ask you to participate a lot more. So I'm going to ask you questions and I'll just wait until someone answers, even if that's awkward. Okay. So let's start with the very basics. What do we mean by semantics? So you've probably heard about syntax and semantics of programming languages. What is the exact line between syntax and semantics? Yeah, this is the part where I expect you to actually talk. Hello? Okay, no one? Okay, can someone please tell me what you think the difference between syntax and semantics is? Oh my God.
Syntax is about the structure of and rules that we actually depend on them to build up a program, and semantics is the meaning of each structure and the syntactical rules.
Right. Okay. But how can we tell if some property is syntactical or semantical? So this was a very general description of syntax and semantics, but is there a fine line? Can we exactly say what's syntactic, what's semantic?
I think a syntactical property is recognized by some predefined grammar, but semantics you need to refer to some other domain of the meaning about the program.
Right. So this was actually a really good answer. So if you can say something, if you can figure out a property based on just the grammar, then it's syntactical. But here's another question. So consider all the compilers that you can get. So suppose that you write a program in C++, and when you want to compile it, there's a compiler error. Can we say that all of these errors are syntactical, or does the compiler also find semantic errors as well?
I think the type errors is a kind of semantic errors.
Yes. So the compiler actually finds some semantic errors for you. One example is the type checking. So if you try to assign, let's say, I don't know, a pointer to a string, you will probably get a type checking error. And that's semantical because that's something that you need to know some meaning of the program before you can reason about it. But is it possible that a compiler does not find a syntactic error? Or do compilers always find all of the syntactic errors? Okay, so I'm going to repeat this. Is it possible that you have a compiler and you write a code that has a syntactic error and the compiler does not complain?
Currently, I think that for the syntactic errors, they are quite hard coded. So a compiler should be able to find all of them. That's my current view.
Right. But that's actually correct. But how about an interpreter? Would an interpreter find all the syntactic errors?
I think the parser will fail if there is any syntactical error.
No, actually, even interpreters these days find all of the syntactic errors. So one good rule of thumb for seeing what's syntactic and what's semantic in case of errors that come out of compilers is to see if an interpreter gives the same error or not. So if you consider, for example, a Python interpreter, uh, the types of errors that you get before runtime is much more limited than a C++ compiler. And all of those extra errors that you get in a C++ compiler are probably semantic. So there might be some tiny exceptions, but that's always the case, almost always. So now this course is mostly, at least the first part of the course is mostly about formal semantics. So when it comes to syntax, we all know that formal syntax is everywhere. We use, for example, grammars such as this one, which is for a simple while programming language that we are going to see over and over again. So in terms of syntax, we are always fine with using formal syntax, but somehow formal semantics came a few decades later. So formal syntax was there since at least 1940s, but formal semantics is something that started to be developed in the 1960s. But here's another thing. Why do we even need formal semantics? And what do we mean by formal? So the second part, what do we mean by formal, is actually the subject of this course, the first half of this course. We're going to talk about different formalisms and say exactly what we mean by that. But why do we need to formalize the semantics of a program anyway? So here's the thing. Consider this simple programming language with this syntax that is defined by this grammar here. Isn't this enough? Wouldn't anyone who sees this syntax just realize what kind of language this is and what it does? Do we really need to define any more formal semantics for this? So I really expect your answer to be yes, but I want you to tell me why. So suppose that we want to only program with this simple programming language that just has if and while. Why do we still need to define formal semantics? So in other
There
words,
needs, I think that there needs to be a structure that the programming language should follow so that it can be interpreted by human beings, no matter what the language is. Just like for human languages like English and Chinese and other languages, we also have some kind of semantics and grammar and structure.
right, yes. So one reason is actually exactly that we want to be able to understand it, and for our own understanding, we definitely need to have semantics. But in case of this simple program, isn't it the case that all of us have the same understanding of this program? Is there anything ambiguous about this programming language? So, and let's say that I know that all of my variables are integers, so that we don't have that ambiguity either. So is there anything ambiguous about this programming language? If I ask you to write compilers for this programming language, would all of your compilers do the same things?
What about the scope of the variable?
I'm sorry, I didn't hear you.
What about the scope of the variable?
Right, but we don't really have functions here. So this is just a language for imperative programs. So all the variables are always in scope. So what I'm asking mostly is that, can we have any ambiguity about how we run if and while, for example?
Yes, I think it is possible because for the if then else, you could do if then, or you could add the braces like if and space then else together, or if then space then else. I think this all possible.
Uh, yes, and actually I can probably give a more concrete example of this. So suppose that I have something like, let me see how I can write on this thing. Okay, suppose I have something like this. If A or B, then so consider this code. There can be different interpretations of this, even though it's a very simple if. So, for example, do you have short circuiting or not? So if I start with this condition and see that actually holds, A is true, would I go ahead and evaluate B, or would I just go to the then part? So that's one example of something that can be totally different in different implementations of this. Uh, so one answer to this can be, okay, if we really want to fix all of our semantics, why don't we just fix a compiler and say that whatever this compiler does is the meaning of the program? So if I want to fix semantics for C++, I just say whatever G++ does or whatever C-lang does. Isn't that good enough? Because there is no ambiguity in what, let's say, GCC does over C, right? So why can't we just say the semantics is what GCC does?
So what about compiler bugs and future optimizations?
Right. So one point is about optimization. So what if the compiler does an optimization that actually changes the program? How can we say if an optimization has changed the program or not? Another thing is what happens if you have several different compilers? So can you say, let's say Microsoft C compiler is wrong because it doesn't match with GCC? What's the point in that? And the most important reason is actually when you write a program. So suppose that you write a program that is 100 lines and you want to prove that this program is correct. So that's the main idea in verification, which is the second part of this course. You don't want to have to rely on the whole compiler in order to just prove that a small program is correct. So when I want to say that this simple program does what it wants to do, I don't want to reason about the entire GCC. So that's another reason why we actually need formal semantics. But then another question would be, what properties should these formal semantics have? So how formal should we be? Because if we want to give really formal semantics that are not compiler dependent, well, we can always do it by giving a Turing machine, right? Uh, but that's going to be really cumbersome. So what do we want from our formal semantics? Some of the things that come to my mind are as follows. So we really need them to be unambiguous. So we have to be able to specify them mathematically, and we have to be able to say if a compiler is actually following the semantics or not. But another thing that we really need is that we need these semantics to be simple enough that humans can actually work with them and reason about their own programs. And also simple enough that we can automate them so that we can have, for example, an automated verifier that proves properties about our programs based on their semantics. But there's actually another really important property that we also need. And can you think of anything? It's probably the most important property that formal semantics should have.
It should be computable.
Well, not necessarily, because we are using this. That was a nice idea, actually. We are using them for reasoning about programs. We are not really using them for running the programs themselves, right? So even if you have semantics that are not strictly computable, that might be fine. So what happens if you have a paradox in your semantics? If you have a case where part of your semantics says that you should do something and another part says that you should do something else. This happened, for example, in Java. basically what we need is that we want our semantics to be checkable and in an automated way. We need to be able to feed our semantics to an automated program that checks whether there are any paradoxes in there. And of course, we want to work with semantics that don't have any paradox. Okay, so in this session, actually, what we're going to do is mostly trying to define semantics for this very simple language. And you will see that even though this language is simple, defining the semantics gets tricky. But before that, let's just do some examples of seeing why we actually need the semantics. So consider this program, which is written in a language that is similar to C++, but it's not necessarily C++. Does this function add two numbers correctly?
I think it doesn't because for x and y, they are unsigned variables. So if you add two unsigned variables together, it could be an overflow.
Right. Okay. That was a great answer. So the first problem that we might have is overflowing. Right.
I think P is uninitialized in this context, which means that
Right.
when you do dereference P, it's undefined behavior. And so the x plus equals y may not always execute.
Okay. So we already have two problems. Do you see any other problems here?
There is a type conversion from unsigned to signed integer.
Right. So that can also go under overflow. So type conversion. Okay. There's one more as well, I think. So the last thing that we also need to check are side effects. Basically, these variables are passed by reference, right? And we are changing x here. So whether this function works correctly or not is really dependent on the formal semantics of the language that we have. For example, the overflow thing, it definitely happens in C++. It doesn't happen in Python, right? This idea that P was not initialized and then we used its value here. Did we actually use the value? Because, well, X and Y are unsigned and we are only checking whether they're greater than or equal to 0. So many C++ compilers would just reach this if see that X is greater than or equal to 0 and not evaluate the rest of it at all. So whether this error happens or not is also dependent on your formal semantics. And then the side effects, whether that's important or not, this is actually dependent on your specification. What do you mean when you say this function adds two numbers correctly? So what we see here is that we don't only need semantics for the language itself, we also need to have a formal specification language for saying what it is that we want to prove. So the problem itself should also be very clear and have a formal semantics. Okay, so this was the first example. Now let me go to another example. So suppose that you have a compiler that wants to do optimization. And let's say that the code that the programmer wrote for you is this, and you want to optimize it to this. What can go wrong?
The variable is accessed by multiple threads. And so this may cause side effects. Although the order of execution is not consistent if there are other threads also using X, or the memory consistency.
Right. So there are problems because of multi-threading, of course, if you have several threads. There are type problems again. So if let's say x is unsigned and it's 0, what happens when you reduce it by 1? And so whether the optimization is correct or not is also completely dependent on the formal semantics of the program. So let's say that I give you some formal semantics. How would you define this problem? So what I want you to do is to formalize the problem first. So when can we say that a compiler optimization is correct? Let's say that we have some semantics for the language. When is an optimization considered to be correct? So there can be different answers to this.
I think it should be for any given input, the optimization result should be the same as the unoptimized version. So it depends on how you define the input. It could be the input should be the required type, or in this case, if you want this optimization to work correctly, we could ask that x must be an integer, like int64 in programming languages. Then we could define that for this optimization, this value should be equal.
Yes. So, but this is assuming that the program actually produces an output, right? There are other cases as well. So we can extend this definition a little bit. So another thing that we can consider in whether the optimization is correct is that if the original program crashes, then the optimized program should also crash, and it should crash with the same error. Or if the original program does not terminate, we want the optimized program to not terminate as well. Right? So again, what this question means is also a matter of semantics, and you have to have a formal definition of the question itself. And this is something that we will mostly see in the second part of the course when we talk about formal verification, when we talk about logics for verification. For example, in LTL verification, we will have a very formal way of specifying what it is that we want to verify. Okay, so let's go to this simple programming language that we have, the while programming language. And everyone's fine with the syntax, right? I don't need to explain the syntax. This is clear? If it's not clear, please tell me now. Okay, so how do we define the semantics for this? One way is to rely on our own intuition about it. So can you guess what this program here does? Any guesses?
I guess it may be computing the reminder.
That's close, actually. It computes the greatest common divisor of x and y. This is the Euclidean algorithm. Okay, so, but how do we know what it does, and how can we completely formalize that? So there are three different methods that are usually used, and the methods are basically called operational semantics, denotational semantics, and axiomatic semantics. And today I'm going to mostly talk about operational semantics. And then using these, we will then in the next sessions try to prove that this program is actually correctly computing the greatest common divisor of x and y. Okay. Before I define the semantics, I need to define what a program state means. So If we think of a program as a Turing machine, it's pretty obvious what we mean by a state. But at the same time, that's not very useful because there are too many details that we don't want to have. So what can be a good definition for a state of our program? So our program has a bunch of variables, and let's assume that these variables all take values that are integers, and let's say that they're not bounded. So they all take their values from the set C. So one definition for a state of a program can be that a state is just a valuation to the variables. A function, this is the valuation function that maps each variable to a number easy. But that doesn't quite catch everything, right? Because it's not just important that what value every variable has, it's also important where in the code we are right now. So actually a very classical way of defining semantics for imperative programming languages is that we define a state as a pair, which is basically a valuation and also some line number saying where in the code we are right now. So if you have these two things, you can actually continue executing the code. This is the approach that we will see again later in the course, but the approach that I like more and we are going to work with right now is the third one. So basically, a state of our program is a valuation to our program variables and also a program. And this program P is the part of code that has to be executed on this valuation. So initially we start with our whole program and some initial value that was given to us. And as we execute it, we are not only changing the valuation, but we are also changing the program itself. So you can think of it like if you have 10 lines of code that are all assignments, when you do the first assignment, you only need to do the other 9. So you can just get rid of that part of the code and just do the other 9. So the definition of
Amir, is there any difference between the second definition and the third one?
Yes, so the main difference is that in the second one, you're keeping the whole code, right? And you're just keeping track of where in the code you are right now. So let me actually do this. So consider a very simple program that just does this. Okay, so at line 1, it just assigns a value to x, and at line 2, it assigns a value to y, right? So when you execute this program, if you have this idea of keeping the line number and the value to the variables, so you can start from an initial state. Let's say my initial state is that I am at line 1 and the value of x is 0 and the value of y is also 0, right? So let's say this is my initial state. Then I basically execute line 1, I go to line 2 and the value of x becomes 1 and the value of y is still 0. So what I'm doing here is that I'm only keeping track of the line number. And in order to do this execution, I have to keep the whole program in memory at all time, right? And especially if this program is, let's say, long and you want to read it in small chunks, this is not really a good idea. But anyway, and then it ends, which is basically, I can show it with a dash that the program has ended and the values will be it. So this is the point of view that says save the line number and the values of the variables. But the point of view that we are going to take today is this one. So the idea here is that we start with a program and the value. So the state itself contains the program. And it contains everything that has to be executed on that initial valuation. So I start with this state. Okay. So my state is that the value of x is 0, the value of y is 0, and I have to execute this code. and then I update it. And the update is that it reduces the number of lines in code, updates X, and now I have this state, right? And then I will get the empty code, 1 and 2. Now, at this point, for such a simple example, these two different views might not seem to be too very similar. But as we go on, especially when we see programs with loops, these things become much more different. So what I want you to really uh, keep in mind right now is that we are using this idea of a state. So whenever I say state, it's not just the program variables and their values, it's also the entire code that has to be executed on that state. Okay. So if I give a name to the set of all states that I have, for example, I call them sigma, then I can basically define what a program execution is. A program execution is just a series of transitions between elements in sigma, right? So, and what is the ultimate semantics of a program? It's if you can just write down all of the executions, all of the possible executions of your program, you have the ultimate semantics. So you can think of the semantics of a program as a graph. And again, this is something that we will come back to. So you can consider a program as basically a graph where the set of vertices is the same as set of states. And the transitions in the program are the edges of the graph. And then the executions of your program will basically be all the walks on this graph or all the paths in this graph. And this graph can completely and without any ambiguity explain the semantics of a program. Okay, but that's for a single program. What happens if we want to do it for a whole programming language? This is where we have to actually define our semantics as rules over these transitions. So the idea is that instead of writing down all the possible transitions that you can have, you just say, okay, I'm going to do a rule-based approach. I'm going to set down a bunch of rules and say that there is a transition from this state to that state only if this rules allow it. Okay, let's do that. And this is what we basically call operational semantics. So the idea of operational semantics is that you define the transitions and you actually define rules that tell you when you can have those transitions. So the semantics are defined in terms of some abstract machine. So let's say that there is an abstract machine that can actually do these transitions. And we don't talk about the transitions themselves at all. So that machine can be a Turing machine, it can be your laptop, it can be anything. The only thing that we care about is that it can do a bunch of transitions over our states. And what we want to do is that we want to set down rules for these transitions. So I use this notation here. Basically, if I have a state where my program is P and the values of my variables are captured by val, then I write this to say that I can transition to another state where the program is P prime and the valuation is val prime. And I also use this notation, which is very common in programming language, and you will see it in all PL papers. So this is a rule. And the way these rules work is that they have a bunch of conditions or preconditions, which we write above the line. And then there are some results which we write below the line. And the idea is that this is just implication. This is saying that if everything that I said above the line holds, then what I say below the line should also hold. So in this case, we don't have any assumptions. We don't need any assumptions here. So it's kind of an axiom. And our first axiom is that if your program is simply skip and you are at some valuation, you can run this program and you will end at the same valuation. This is the most obvious thing ever. And Note that this is also a state. So when the program has ended and there is nothing else left to execute, I just don't write the program. So this rule is super clear. So the next rule is also very simple. So let's say my program is uh, just one command assigning a to x. And let's say that a is some expression over my variables. And I want to run it starting from the valuation val. So what can I do? Well, I take a and I find its value according to val. So for example, a can be something like 2x plus 3y. And I just look at my valuation, see what are the values of x and y, and put them into a and compute the value of a. And let's say the value of a in my current valuation is c. So c is a concrete value. A itself was an expression, but c is now a concrete value. So what I can do is that I can transition from the state where I had to run this command and the valuation was val to a state where I don't have to run any more commands and the valuation is the same as before, except that the value of x is now c. So this is also super easy. And the only reason that I want you to see this is because I want you to get familiar with the notation. So let's go to our other commands. This is where the meat
Excuse me,
comes.
sir.
Sure.
Sorry. Excuse me. So,
Yes.
so the square bracket after the val, I mean, in the second rule, under the line, like for the square bracket after the val, it means that append the value c, or I mean append the fact that the x is now c to the existence.
No. Okay. This is actually not like that. So it's completely logical. The idea is that so this part here. So the double square bracket around a means the concrete value of a, the valuation of a. So
Okay.
a itself is an expression. So it can be anything. For example, it's 2x plus y. And then because we have a valuation val for our variables, so for example, I know that x is 2 and y is 1, then I can actually compute the concrete value of a, right?
Okay.
So what this rule says is that if the concrete value of a at the current valuation val is equal to c, then you can have this transition.
Okay.
And by the way, I could write this just above the line here because I can use it as a hypothesis. But usually we consider these to be side conditions because I want to only have this kind of expressions in my rules. So that's why I put it on the right-hand side instead of actually putting it up here. It doesn't really matter, and some people just put it up there.
Okay, I mean, like, what about the square bracket? Like, yeah.
Yes. So this is the notation. Yeah, the square bracket a, this whole thing.
Yeah.
Like, a square bracket a parenthesis val means the value of a when it's evaluated using the values in val.
Okay. Okay. Thank you.
Yeah. Okay. And this one, I think, well, I can't point to it. I don't know why. There's a bug here. So this part, this basically means the same valuation as val, except that we put the value of c for x.
Okay.
Right? So what is val? Val itself is a function that maps every variable to a value, right? That's what we use for evaluation. So here what I'm saying is that keep the values of all variables except that change the value of x to c.
Okay, I get it. Thank you. Thank you.
Yes, so this is just a matter of notation and you will get used to these notations very soon. Okay,
thank you.
Now I want to write rules for the other structures that we have in this language. So the first structure after skip and assignment is this, the sequential composition. So I'm going to write one of the rules and then I'm going to ask you to write the other rule. So if I have a, so what does this assumption say? It says that you have a program P that if it runs on the valuation val, it will terminate with valuation val prime. In one step, it will terminate, right? Because with one transition, we got to a state where we don't have a program anymore. So if I have this as my hypothesis, and if I have this situation, a situation where I have to run P and then Q, and I'm starting with the same valuation. So it's easy to see that I can just transition to a case where I have to run Q and I have val prime. Does this make sense? So if you had to run P on the valuation val, in one step you would terminate and get val prime. But now you have to run P and then Q. So in one step you will get val prime and you have to run Q. So if you have this transition above the line here, then you will have this transition below the line. And this is our rule. Our rule says that whenever you have this transition, you can be sure that you also have this transition. Okay? But we also need another rule. What other rule do we need for sequential composition? So this was the case where the program P on the valuation val was terminating in one step, right? What if it doesn't terminate in one step? So in that case, I will have P and the valuation val. Put that here. And it's not terminating in one step. So what happens when I run one step of it, I get some P prime and some new valuation. Okay, in this case, can I do something similar here? So what should I write after this arrow here? Okay, just to make sure, everyone understands the notation, right?
Is it a P prime semicolon Q comma val prime?
Yes, exactly. Because basically the execution of P is going to continue, and in one step we got to P prime. So down here we had to run Q after P, so now we have to run Q after P prime, right? So does this make sense to everyone until this point? If you don't understand anything, please say now. Okay, so the notation is clear to everyone. What should we do for if? So you can use the chat to actually give me some suggestions for the rules that we can write for an if statement. So just let's go back, take a look at these rules. These rules are basically defining the meaning of a semicolon, the meaning of sequential composition. And now I want to do something similar with if. So can you give me rules for if?
I think it should be a transition from the variable. For example, in the syntax, we have if b, so it should be a transition from if b to the body. Yeah, I think.
Right. So we know that on the bottom side, we will have something like this. Right. So I want to define transitions out of this state. But what should be the definition? What should be the rule? So P and E. Okay. Yes, we're getting 3 right answers. That's great. Yes. So we do a case analysis on the if condition, right? So what does the case analysis on the if condition look like? It's actually quite easy. Again, we have to evaluate B. So we say if B is true at this initial valuation, then what do we know? We know that we have to do P, right? So this will just go to P and that. So this is our first rule. The rule is basically if you have to run this if condition on this valuation and in this valuation you see that the if condition holds, then you basically only have to run the then part and the else part doesn't matter. And the other rule is also very similar. So if this thing is false, then you will have to just run the else part and the then part doesn't matter. Okay, these weren't too hard. What happens next? We also have a while. So what should we do with while? Any ideas? So we want to formally define what a while loop does in terms of rules for the transitions that are allowed. What kind of rule can we use? So we can actually do a case analysis on the while itself, right? On the while condition. So if I have something like while B do P and I start with evaluation val. Okay. So I can do a case analysis again. And the first case that I want to consider is if B is true. What happens if B is true? So yes, that's actually correct. Yes. So if B is true, we know that we do P, and then we still have to do the while again, right? So it would just go to okay. Does this rule make sense to everyone? So the idea here is that if you want to run, if you start with an initial valuation val and you want to run while B do P, and if it happens that the condition of the while actually holds, so you have to do P first, and then you have to do the whole while thing again. So you will have a rule like this. And now the nice thing about this is that this is actually a recursive rule. So basically, when you are running a program, when you are running this, for example, in an execution, you first make it larger, and then you run the P part, and then you again have to run this. So the rule itself is actually showing us a very nice theorem that was known since the early days of computer science, that having a while is just as powerful as having recursion, because we are basically defining the while recursively. Okay, what is the other case? So what happens if the condition is false? So what kind of rule should I put here? My condition is false.
Bottom just becomes val.
Yes. So I really have a hard time working with my mouse. So if you have a while condition, if you have a while loop, and that's all the program that you have, and if the condition doesn't hold, well, you don't have to do anything, and the program just terminates at that point. Okay. So yes, we can also do skip. That's also absolutely fine. You can also say it becomes skip. Well, but then in the next step, it will just become valid. So. Okay. Now, what if I don't want to do this kind of casework? Can I write something like this? So let's say I have the same state, and let's write it the way that probably all of us learned how while works, which is we say if p to p skip p, and then it doesn't really fit. But can I write a rule like this? So basically, this is called unrolling the while loop. What I'm doing is that I'm taking out its first iteration and adding it as an if condition, saying that if B holds, then do P, and then I'm doing the while again. Is this rule correct? If you think this rule is correct, write yes in the chat. Just want to do a poll and see. Okay, 2, 3. Okay. If you think there is something wrong with this rule right now, okay. What's wrong with the rule?
So what if B is false? Then the skip will be the statement to be executed, and then the while loop will again be checked. So it will be just a loop checking for the while loop.
Right. Yes. Okay. So basically what happens is that if we have this incorrect rule in our semantics, whenever you have a while, you're saying that your program never terminates. And you can actually even see that with a syntactic analysis of the rule itself, because we never get rid of the while, right? So if you only look syntactically, we have a while here and the while is preserved. So we will never get to a point where the program terminates. So this is not a good rule for us, even though intuitively it makes sense. Okay, so let's continue with this. Now I want to extend my programming language, and I want to extend it with two different new structs. So the first thing I want to add is non-determinism. And non-determinism is something that you might have seen before. Basically, the idea is that the program has a choice. It can do one of two things. And we show it with a star here. So for example, if I have a program that says, I don't know how to get that star thingy. If I have this kind of program, this kind of command in a line of my program, what it means is that either do the first thing, either assign 2 to x or assign 1 to y. And we don't know which one happens, but one of them will happen. Okay. And why are we looking into non-determinism? Well, we will see many use cases later, but what's really interesting for me right now is to be able to write programs that have different execution paths on a single initial valuation. So if you look at the rules that we have here, it's actually easy to prove that, sorry, you're on this screen. So if you look at the rules that we wrote for the while programming language, it's easy to see that from any initial valuation, we are defining a unique run of the program, a unique execution of the program. And now what I want to do is that I want to have this kind of structure so that I can have different executions for the same program on the same initial valuation. Okay, so how would you define rules for such a structure, for this non-deterministic choice?
Can you clarify what the line exactly means again, please?
So it means that when the program gets here, it either does the first thing or the second thing. And we don't know which. So let's say that there is an evil genius that controls which one happens. So for example, we can use this to model an input from the user. So if, for example, at some point I have, let's say, a variable x that can get value 0 or 1, and if I take it as input, because I don't really have an input mechanism in this simple language here, I can just model it as non-determinism. I can say that someone is choosing whether this first thing should happen, whether 1 should be assigned to x or 0 should be assigned to x. But I don't know what the choice would be. So I will have different possible executions from this point. And I want to write rules that actually capture this.
Okay, thank you.
So it's not exactly random, because when you say random, it means that, and I'm answering the question in chat if you're not seeing it. So when you say random, it means that you actually have a probability measure. And here it's not the case. We just know that one of these things will happen. We don't know which one, and we don't know what the probability of each choice is. So it's a bit different from randomness.
Can't
Okay.
we write the rule with if and conditional?
How? So
maybe we should consider some variables or some states, and based on that to be true or false, either of these two can happen, and then we can just rewrite the, I mean, result. We can write the result.
Yes, I think that's workable, but there is actually a much simpler way. So
okay,
let's do this. Let's say that I have a non-deterministic choice between P and Q at evaluation val. Well, what does a non-deterministic choice mean? It means that, yes, that's actually correct. So a non-deterministic choice means that I can choose the first one. I can choose to run P. So if I have the premise that running P on val would lead to, let's say, P prime val prime, then I can do the same thing here, right? I can say it is possible that P is chosen. So if there is a transition from P val to P prime val prime, then there would also be a transition from P star Q val to P prime val prime. And the same thing for Q. So if you have this, you will have okay. Now this is the part where for some of you actually this formal definition makes things much easier to understand. So understanding non-determinism on its own might have been harder than understanding these rules. So the rules actually give a really nice definition of what it means to have non-deterministic choice. It basically means you either do this or do that. Okay, and I also want to add another thing to my programming language. I want to add a halt, and think of this halt as basically something like a return or something like exit 0 in C++. It just ends the program instantly. So how would we go on defining a halt statement? So you see the problem that we have right now. When we get to halt, it's like you have to also ignore all of the other pieces of code that you have because you've reached halt and it's the end of the program. You just have to end it there. So yes, that's actually correct. So the first thing is that if you have halt and some valuation, then it's pretty much like a skip. It's just the program ends with the same valuation. But there is also this other thing that if you have halt and then you have something else, it doesn't matter what else you have in your program. As soon as you got to halt, it's the end of the program and you just end with the valuation. But now the important point here is this. As soon as you do this, you have to also update your rules for sequential composition. So going back to this slide, see here we had a rule, we had two different rules for sequential composition. And the rule that we have with halt is actually in contradiction with these, right? Because right now, what we have here is, it says that if you have halt and then a program P, you have to basically terminate with the same valuation val. But then this also comes under the jurisdiction of this other rule that we had here, this thing, right? Because consider that P is halt. Then P and val will go to some P prime val where P prime is empty and val prime is just val. So this rule says we have to do something different. And this is the kind of contradiction that you will invariably see when you are writing these rules, and you have to be very careful with these contradictions. So the way we solve this is by adding another side condition, basically saying that this only holds if P is not halt. Right? And also for the other one. Now, again, another important reason why we do these things so formally and actually write down these formal rules is because then we can use an automated theorem prover, something like Koch or Isabel, to tell us whether our rules are contradictory. And in this case, the initial rule was contradictory with the rule for halt. Okay. So yes, that's done. So I'm going to give you a small homework now, and this is due a week from now. So I want you to consider this slightly extended program. So we did until this part, but now I want you to also write rules for break, continue, and also for a for loop. And I've given you the syntax here, and I want you to define the formal semantics. And of course, as you do this, you might have to go back and redefine some things. You might have to change some of the rules. And you might even have to change the meaning of a state. So just think about this. What we saw today is what we call structural operational semantics. And structural operational semantics was initially defined by Gordon Plotkin in this really game-changing paper. And this is one of the papers that I would ask you to read. So until the end of the semester, I will probably ask you to read 3 papers. And this is one of them. It's a long paper, so you have a lot of time to read it. You will probably know a lot of the topics that are covered in this paper because it also talks about basic automata and stuff, so you can skip those. And what this due date means is that from that date onward, I assume that you know the material in that paper. So you don't really have to turn in anything. Okay. So I actually have a lot of other things to say, but I will probably run out of time.
Excuse
now.
me, I have a question about the last
Sure.
semantic of halt. Could you go to that slide?
Yes.
So basically, I'm confused because for a program to be halt, it means everything is disappeared, or you mean that the halt is just mean it stops and it keeps everything there?
Yes, it basically, well, you can also define it that as if it makes everything 0. So we can define halt to say that it erases the memory and the value of all variables becomes 0. But what I meant here was that just the execution of the program halts.
Okay, I see.
So
just
the variables are
0.
exactly what they were before.
Okay, yeah, I see. Thank you.
Okay. Any other questions?
Can you share some book or some reading material that we can read for more clarification or to learn more?
Yes, that's this paper. What was that? So this paper is actually very similar to a book. It's 150 pages and it goes into excruciating detail for everything.
Okay, thank you.
Okay. Um,
Sorry, I want to ask, will you share this PowerPoint?
yes, definitely.
Thanks.
Well, it's not actually PowerPoint. It's a downgraded thing called Jamboard by Google, and I hate myself for using it because it's so buggy. Okay, but let me just give you a preview of what comes next. So next we're going to look into the semantics of expressions as well. So until this point, we just assume that we know what expressions mean and we use the evaluation of an expression, but of course we have to define that formally as well. And then we're going to see something called big step operational semantics. So the operational semantics that we saw today are called structural operational semantics or small step operational semantics. And the idea is that the rules basically define transitions that correspond to one step of execution. But then later on, we will define these other rules that will capture all of the execution of the program in a single rule. And that's called big step or natural semantics. And I don't know why they call it natural, because this is much more natural than that. But we will see that. And yeah, that's all for today. If you have any other questions, please feel free to ask.
Actually, I have one more question. Sorry. It's that I just want to ask whether semantic rules actually can they have precedence, like which semantic rules goes first, or must they be like unique?
So you can do that, but that's actually a way of making sure that there are no inconsistencies in the rules. It's a lazy way of doing that, saying that you apply this rule before that rule. But honestly, it makes life much harder, and it's better if you just make sure that the rules are consistent and they don't cover the same case.
Okay, thank you.
Yeah, so basically the rules have a very well-defined logical meaning. It means that if this transition exists, then that other transition also exists, right? So you can write as many of these as you want and in any way you want.
I have a question about the notation. I don't know when should we add as a condition as the right side of the line.
Oh
Because,
yeah, that's not really an important distinction. So the right side of the line and above the line are the same thing. Usually it's that people want to put conditions that they think are more important above the line. So in this case, I put conditions that have these arrows in them above the line, and I put every other condition on the right side. But it doesn't really matter. The logical meaning is the same. You can just take this one and put it up there.
Okay, and I have another question about the, it's not about the semantic, it's about the syntax. Given the language with in the context defined in this page, it is possible to find a way to figure out the all kinds of syntax errors with arbitrary programs, as long as the program obeys to this syntax.
So basically, the idea is that we define semantics only for programs that are syntactically correct. So we assume that a syntactic check has been done before, and we assume that our universe is just the universe of syntactically correct programs and define semantics only for them. Because, well, and this is also a natural choice. If a program has a syntactic error, it's meaningless, right? So it doesn't make sense to define semantics for it.
So it's possible to solve this to solve this problem, that checking the syntax to check the program is syntax valid by algorithm. It is a decidable problem or not.
Yes, of course, because we have context-free grammars, right? And uh, that's actually something that is probably more in the realm of people in compilers. So if you have a context-free grammar or many other types of grammars, you can basically easily check whether a given string fits into that grammar or not.
Okay, I see.
But one thing that we can do, what no one does, is to actually write the syntactic check as rules as well. But that would make life much harder. I wouldn't want to do that. So let's just assume that everything is syntactically correct. Okay. Any other questions?
Can you share some past paper if you have one?
Some what paper?
A past paper of this course. It will be good to know like what we're expected in the end.
Oh, okay, sure.
Thank you.
So I will put on Canvas. I will put everything on Canvas. Okay. So that's all for today, and see you all on Thursday.
Professor, for the homework, how should we specify the first loop after the break or continue state?
Sorry, I didn't hear you well. How should we specify what?
Sorry, how can we specify the first, for example, while loop after a break or continue statement? So because if we want to specify
yes,
paper.
That's the tricky part of the homework. You have to figure it out.
Oh, okay, thank you.
Yes, but when you submit your responses, if it doesn't work, we will give you comments and tips.
To clarify, like I meant the past exam paper. If you can share one, that will be great.
Oh, so, sorry. That's not gonna happen because this is the first offering of this course.
Oh, okay.
Yeah. But again, the exam itself would be super easy because you will have 2-3 days to think about everything.
Okay, thank you.
Okay, have a good day, people. You can leave.